Hello to everyone. My name is Giovanni Morlino. I am a researcher at the National Institute for Astrophysics in Florence, Italy. In this presentation, I want to discuss a little bit how recent and high-detailed measurement of the cosmic ray spectrum are changing our understanding on how particles propagate inside the galactic halo. This work is mainly based on this paper here. So what we know about the propagation of cosmic ray is mainly obtained by from the information on the secondary over primary cosmic ray flux. When cosmic ray propagates inside the galaxy, they suffer spallation processes producing secondary nuclei, like carbon nuclei hitting on a proton of the ISM, producing a boron. Now, measuring the flux of boron over carbon, we are able to infer the amount of grammage that particle have to traverse before reaching the Earth. And this provides a direct estimate of the residence time of particle inside the galaxy if we know the average gas density inside the galaxy. Now, considering that the typical cross time to cross the halo thickness is for a particle doing a ballistic motion is only of the order of a few thousand years, sorry. But the escaping time obtained from measuring the secondary over primary ratio is of the order, a GV energy is of the order of 100 million years. So it's clear that particles cannot propagate along straight lines, they have to diffuse. So the basic picture that we have in mind discussing particle diffusion is the one proposed by Ginzburg and Zhirovsky in the late 60s, and is still that one. So essentially particles are thought to be produced inside the galactic disk by some sources, like for example supernova remnant, and they start to propagate not only inside the disk, but in a larger halo, larger than the galaxy, whose typical thickness has to be of the order of a few kiloparsecs. So the diffusion inside this bigger region is assumed to be constant, and the escaping time in this kind of system is equal to the square root, to the square of the thickness of the halo divided by diffusion coefficient. From boron over carbon, we can infer the energy dependence of the diffusion coefficient, which has to be proportional roughly to e to 1/3, suggesting the presence of Kolmogorov turbulence. Now, this picture isn't satisfactory for at least two reasons. First of all, we have to explain what generates the diffusion of particles. And second, we also have to understand which is the physical meaning of H, of the thickness of the halo. Now, coming to the diffusion, we know that the interstellar medium is turbulent, and measuring the density of electrons, we infer that there is turbulence, which is roughly Kolmogorov turbulence on a very wide range of scales. We can assume in our model that also the magnetic field follows the distribution of electrons, because the density of electrons is a passive tracer of magnetic field. And we assume that the turbulence of magnetic field is Kolmogorov-like, and also it is of Alfvénic type. The turbulence is injected by supernova, which inject turbulence at typical scale of tens of parsecs. And the typical normalization of the energy of magnetic turbulence compared to the energy of the large-scale magnetic field is of the order of 10%. All these assumptions are needed to explain the diffusion of galactic cosmic rays. So once we have described the turbulence, now we can derive the diffusion coefficient of particles, assuming that delta B over B is much smaller than 1. We can use the quasi-linear theory in order to calculate the diffusion coefficient. And what we get is that the particle diffuse essentially due to this resonance scattering. They diffuse in a way parallel to the magnetic field, and the diffusion coefficient, the parallel one, is equal to the Bohm diffusion coefficient divided by the power at resonant waves. estimating this diffusion coefficient in the case of the interstellar medium of our galaxy, we get an equation which is this following here, which is of the order 10 to 29 centimeters squared per second with an energy dependence of E to 1/3. This is called the Kolmogorov diffusion coefficient. So just as a reference, the power in waves for waves that resonate with TeV particles is of the order of 10 to -4 the energy of a large magnetic field. This means that even if the power in this wave is very small, this can affect strongly the diffusion of particles. So the first problem of this picture is the anisotropic turbulent cascade. It has been shown by Schrieder and Goldrake that the galvanic turbulence cascade in an anisotropic wave, meaning that the majority of the power after a while is converted in perpendicular modes rather than parallel modes. But now the most effective way to scatter particles is through parallel modes. The perpendicular modes, perpendicular meaning perpendicular to the large scale magnetic field, those modes are not effective in scattering particles. So this means that at small scale, for particle lower energy, there is not enough power to scatter particles. The second problem arises from measurement of cosmic ray spectrum. Recent measurement by Pamela and MS, and also confirmed by other experiments like Attic, CREAM, Calade, Nuclei, and Dampe, have revealed that a rigidity of roughly 300 gigavolts, all cosmic ray spectra, all species are showing an hardening of the spectrum. So this means that the spectrum is no more a simple power law as we were used to think. And because of the spectrum is essentially a function of the injected spectrum Q Sn divided by the diffusion coefficient, this means that either we have to change, we have to put a break inside the injected spectrum, or we have to change the diffusion. Now, the same measurement from MS02 of secondary nuclei is showing that the break in secondary nuclei is twice the break in the primary nuclei. And this is supporting the idea that the break has to be inside the diffusion coefficient and not inside the injected spectrum. This because the secondary spectrum, the spectrum of secondary nuclei, depends twice on the escaping time. So depends twice on the diffusion coefficient. Now let's make a step forward. Let's include in the model of diffusion of particles the resonance streaming instability. Now, when particles are trying to escape from the galactic disk, there is a gradient, and because of this gradient, a particle can excite alpha waves that resonate with their own. The growth rate of those particles is proportional to the gradient of the pressure of cosmic rays. Now, the same waves that are produced by cosmic ray can be damped by nonlinear processes, and the typical damping rate that one can estimate is proportional to the square root of power times the Alvan velocity. Now, equating the growth rate with the damping rate, we can get the density of waves produced by resonance streaming instability and the corresponding diffusion coefficient. In this game, we are assuming, in order to calculate the growth rate due to streaming instability, we are assuming the cosmic ray spectrum observed at the Earth. Doing this exercise, we infer a diffusion coefficient which has a normalization, which is very close to the one inferred from boron over carbon, and the slope which is different from the Kolmogorov one. So the first consideration is telling us that the streaming instability probably has to play a role in the propagation of cosmic ray into the galaxy. So now with this ingredient, we want to build a more consistent model with inclusion from one side of large-scale turbulence injected by supernova remnant. These large-scale turbulence injected inside the plane suffer not only the cascading that we have described, but also advection. So we want to put this further ingredient because it's very important, because once you put the advection along the vertical direction with respect to the galactic plane, what happens is that we can now estimate a physical dimension for the galactic disk. In fact, for the galactic halo. In fact, comparing equating the cascading time with the advection time, we can infer a typical halo thickness of the order of a kiloparsec. And this is a very this is compatible with what we need from a measurement of boron over carbon. On top of the large-scale magnetic turbulence, we add the streaming instability, so turbulence produced by cosmic ray themselves. And in this way, we build a full magnetized halo, which has turbulence at all scales. Using this turbulence, we now can estimate the diffusion coefficient. In this plot, I'm showing using a nonlinear model to describe the generation of turbulence and the propagation of cosmic rays. I'm showing the spectrum of turbulence. Different lines are showing different distance from the galaxy, from the galactic plane. With red, there is the turbulence only inside the galaxy, with other lines are showing turbulence at larger distances from the galactic plane. Dotted lines are showing the turbulence only due to the Kolmogorov cascade, while solid lines are showing what happens when we also add the contribution due to streaming instability. And you can see that for large K, these contributions are dominating the diffusion. And this on the right, you can see the corresponding diffusion coefficient at different distance from the galactic plane. So the conclusion is that self-generated diffusion can dominate the transport for energy below 100 GeV. And inside this turbulence, we can calculate the spectrum of protons, and this is the result, essentially compared with the AMS observation. And you see that the data can be very well explained by this model, including the break measured at 300 GeV. And here we can distinguish three different regimes. A regime between 10 GeV, where transport is dominated by advection, an intermediate regime where transport is dominated by self-generated turbulence, and a regime where transport is dominated by large-scale turbulence. The same model also works very well for explaining the spectrum of other nuclei. This has been shown in this paper here. But surprises are not finished. In fact, a very recent measurement of the cosmic ray proton spectrum above few TeV by the Dampe experiment has revealed that there is a further softening of the spectrum above 10 TeV. Hints were already present in other experiments like CRIM and nucleon, but with larger error bars. And existing measurement, always by CRIM and nucleon, are suggesting that a similar softening is also present in the helium spectrum. So this is possible, an indication that we further need another change in the transport regime, or probably there is some other ingredient. This is still a matter of discussion. It is, however, very interesting now to try to understand how the cosmic ray spectrum should behave from 10 TeV up to the Ni region. Now, unfortunately, above a few hundreds of TeV, we don't have a direct measurement of cosmic ray spectrum. We have to rely on the experiment done with extensive ice showers. Now, unfortunately, this kind of experiment has large uncertainties, and in fact, there are essentially two different bunch of results. One provided by the Cascade experiment, which is this collection of data here, and the other by IceTop, IceCube, which are measuring a larger flux around PV energy. This is the composition of the light component of the cosmic ray spectrum. Now, assuming that this is essentially dominated by protons, the conclusion is that if Cascade is right, the cosmic ray spectrum is compatible with a single power law since from 10 TeV up to PV energy. While if IceTop is right, we need a further hardening of the spectrum somewhere in this energy range. The answer to this problem will be probably come in few years. In fact, in the 2025, the experiment HERD is planned to fly on the China's space station and with an extended lifetime of 10 years. The exposure of this experiment is very large for a direct cosmic ray experiment with a 12 square meter per steradian per year, and it will be able to measure the primary spectra of protons and helium up to 3 PeV with 50% energy resolution. So we will have an answer to this point. The last point I want to discuss is the rule of unstable nuclei. So unstable nuclei in the cosmic rays can be used to estimate in an independent way the residence time of particles inside the galaxy, disentangling the value of the thickness of the halo from the diffusion coefficient. Beryllium-10 is especially useful in this game because it's a long lifetime of 1.4 mega years. Now, beryllium-10 is decaying in boron, and we do expect that the flux of beryllium is suppressed at smaller energies, such that the decay time at this energy is smaller than the escaping time from the galaxy. And we do expect for typical value parameters that this suppression should occur at rigidities below 100 gigavolt. So the measurement of MS02 is not able to disentangle between different isotopes, so like beryllium-10 versus beryllium-9. So we can use the total measurement of beryllium, including all isotopes, divided by the measurement of boron. This ratio is also sensitive to the decay, and you can see the data here, the plot on the right, compared with different curves where we are changing the size of the halo. You see that data are compatible with having a size of the halo larger than 5 kiloparsecs. A different analysis also using the same data support a typical size of 5 kiloparsecs with quite a large uncertainties, however. And the uncertainties is connected to the fact that this measurement is very sensitive to the uncertainties in the spallation cross-section, which is quite large for beryllium. In order to overcome this problem, we can hope to measure the beryllium-9 over beryllium-10 or over beryllium-9 ratio. This ratio is less sensitive to the spallation cross-section uncertainties because the ratio inside the ratio uncertainties cancel. And but present measurements are limited to small energy range below GeV. And are affected by larger bars. However, I want to notice that recent reanalysis of Pamela data has been able to, done by Cernetti and Nozzoli, has been used to infer a size of the halo which is even larger than 5 kiloparsec. But still the uncertainty is quite large. But in the near future, a new balloon-borne experiment called Helix should fly next year, and we'll measure the ratio of beryllium-10 over beryllium-9 with unprecedented resolution up to an energy of 10 GeV per nucleon. And this will be very useful in order to disentangle models that have different halo size. Okay, with this consideration, I will come to my conclusions. We can say that high precision measurement of cosmic ray data are changing our understanding of the physics of cosmic ray propagation. And the real news is that now cosmic ray spectrum is not anymore a single power law. We can say that there is a spectral feature almost at every decade in energy. The halo diffusion model still remains a valid framework to explain the cosmic ray data, but cosmic ray transport is more complex than what previously thought. The size of the halo is probably a consequence of the balance between advection and wave damping. The self-generated turbulence is probably needed to explain the scattering of particles at energy below 300 GeV, and the energy range between 10 TeV and PeV, which is still unexplored in the measurement of single component, is probably hiding more surprises. Finally, unstable nuclei can be used to measure the residence time in an independent way from boron over carbon, so disentangling diffusion versus the halo sides. Present MS02 data on beryllium favors an halo thickness between 3 and 8 kiloparsec, but future experiment like balloon bond experiment will reduce the uncertainties down to 10%. So we will have much more precise measurement of the thickness of the halo. That's all from my side. Thank you very much.